Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, I'm very pleased today to introduce George Varghese visiting with us from University of California at San Diego. He's been here with us for about a week and a half, and he'll be here for another week and a half, so if you'd like to chat with him, please send him an email and set up a time. George has a very long background of doing very novel and innovative things, combining algorithms and network hardware, getting tremendous performance out of systems that people didn't think were possible, and he's going to be sharing some of those insights with us today.
Thanks, Dave.
Thanks, George.
All right, so I call this talk The Edge, Randomized Algorithms for Network Monitoring, and if the title sounds a little like some kind of band, don't worry, we'll try to explain what The Edge means. And there are two main themes in this talk, right? One is that for hardware people, they're so used to the deterministic drum of a clock that randomized algorithms actually are surprising to them, that they can actually be done. And so when we went to Cisco, we actually found that there was a culture change that had to be done, but it can be done. And sometimes when it really gives you benefits, then people will consider doing it. And the second thing is that I've spent a lot of my life trying to make networking hardware fast. And the main functions were pushing packets and trying to do packet classification and lookups. But increasingly, I'm beginning to think that the next generation of problems is in monitoring and trying to figure out how well a network is doing. Okay, so those are the two themes, and I'm going to try and tell you more. So to explain these themes, right, when the internet first started, it was this very simple network where everybody knew each other. They called up each other when there was trouble, and they had long hair too. And the main problem was to try to make it more flexible, try to make sure that it was fast, and try to make sure it was scalable. Okay, so I guess they succeeded, right? It's pretty flexible. It runs all kinds of things. It's pretty big. It's pretty fast, right? But it's complicated, right? And so the big problems now are things like overloads. The symptoms of success. You know, it's like when people after a certain point they have blood pressure, and you know, it's often the symptoms overloads, attacks, and failures. So the next, if you look at measurement and control, surprisingly in the internet, there is nothing built in for measurement and control. Okay, even things like traceroute, which you may have heard of, were kind of hacked after the fact, right? And using completely unsuspected mechanisms for those things. And so the claim here, though, is that you would like engineered solutions. And the current generation of router vendors are open to this, because it turns out that routing has become commoditized, and there is Broadcom and various Marvell who are selling these chips, and so almost anybody can build a router today. So the router vendors are actually open now to say, okay, I'd like to add these features that would differentiate myself from other things. And if you look at sophisticated systems like the Boeing 747 or bridges, today almost everybody builds in sort of control things. So it's the natural thing to be more autonomic, to be more, okay. So this talk, though, is also going to talk about this other theme of using randomized algorithms, right, in network chips for basically doing these kind of engineered solutions for performance and monitoring. And since this is a very general thing, okay, I'd like to sort of give you three specific instances. And I know there are theoreticians in this audience, and I think each of these three problems can be abstracted and encapsulated very simply. And I will try to show you the relevance to the real systems problems. The first one is a well-studied one, okay, but I just illustrated just very quickly to illustrate the benefits and the edge of a randomized algorithm. Finding heavy bandwidth flows or heavy hitters, very common. I think most theoreticians know this. The second one is measuring microsecond latencies in networks, and that's a little surprising for people who think of the internet as being a millisecond or even a second. And the third problem is logging all infected nodes during an attack, given certain constraints like limited memory and bandwidth. Okay, so those are three problems, and the main, from the theoretician's point of view, and this is where the edge comes in. Okay, in each case, a simple sampling scheme will do the job. Okay. The only thing, though, is that if you add a little bit of hardware and put in a little bit of processing in the router, you get an edge. You do something better in some quantifiably better way. Okay, and that's what I mean by the edge. Okay, so and I'm going to try to demonstrate the edge, and at the end, what is common to all of these is I'll show you the edge over simple sampling. Okay, so wait for that. But but so let's just start focusing on there are some rules here that we have that are different from standard algorithms. Okay, so we need to sort of specify the rules of the game. So the first rule of the game is that we have comparatively small amounts of memory. Okay, if you're used to a PC and you think of the infinite amount of memory a PC has, you say, what is the problem? Why are these guys worried? But it turns out that in routers, often we have to do everything on chip. And so it's more like cache memory, which is always limited at every level of technology. Okay? So it's not like we have 10 registers. It's on-chip cache, so it is on-chip SRAM. And so we have maybe, like numbers like 32 megabits, which is quite a bit. But nevertheless, it's not scaling with the number of concurrent internet flows, so you can't just sort of remember everybody. So you have to do something smarter than just remembering everybody. Okay? Also, we have very little processing. I like to tell people that we are in the region of constant time complexity. Order log n is slow for us, right? So if you look at the memories we have, right, a 40-byte packet has 8 nanoseconds to be processed. Even the most aggressive on-chip memory is like 1 nanosecond. So you get 8 reads or writes to memory. Okay, now that's cheating a little bit because there's a certain amount of parallelism. You can do some things in parallel, but I haven't seen chips with more than a factor of 30 parallelism. So from beginning to end, you get 240 reads or writes to memory. Okay, so it's a very limited canvas that you have, and within that canvas, you have to do very simple things. Yes.
I just wanted to ask, in general in this field, 40 bytes is the absolute worst case. Are people actually designing hardware for 40 bytes?
Yes.
Or are they designing? Okay.
Yes, they do. So you could argue that that's not the right thing. Okay, but they have tests today called light speed, and light reading has a certain test where they'll do bake-offs between Cisco and Juniper routers, and if one of them fails the wire speed test, then there's big news. And do customers not buy? Everybody seems to have bought into this Kool-Aid. So you can argue that, but that's a whole other topic. So let's just believe this for now, and whatever it is, there is some number that can.
So stunningly large number of packets are AX, which are pretty close.
Half the packets are AX,
yeah.
Right? 50% of the packets are AX. So that's a good point. Yeah. Do you have a question? Yeah. Okay. All right. So let's start with the specific problem, right? All the generalities, let's do, and this is a very simple problem. And so the problem is what is called heavy hitters, and you are a router and you're sitting here and you're watching a stream of packets flow through you, and the packets have some key. And let's assume it's a source address. Okay? So as they're marching to you, you see S2, S1, S5, S2, S6, S2. And if you had plenty of memory or you just omnisciently looked at the stream, it's easy to see that S2 is occurring quite often, right, compared to the rest. And so S2 is a heavy hitter, an elephant, and the rest are mice. All right. Now we know that if we had memory for all of them, a simple hash table suffices. Every time we see a new source address, we start a new entry, and then we bump a counter every time we see a source address again. And at the end of the interval, we see S2 is 3, and if the threshold is, say, 2, right, we declare S2 is the heavy hitter, and we're done. Okay? The problem is, by our constraints, we do not have memory for all the possible source addresses. We could have millions of source addresses in a second interval. Right? So what we would like to do is somehow directly extract, right, the heavy hitters without storing all of them. Okay? And this is a well-known problem. Okay? So let's just now here's where the statistician comes in and says, oh, that's easy. I simply sample. Right? I basically, depending on the size of my memory, and let's say I have 10,000 pieces of memory and 1 million flows, I could sample at maybe 1 in 100 or 1 in 1,000, and with high probability, the heavy people will float into my sample. And I can count how many times they occur in the sample and scale up by the inverse of the sampling factor to estimate how much they sent. Okay? But there's a lot of variance in that estimate of the amount they sent. You don't just want to find them, but you want to find out how much they did. Now, we have a very, very simple scheme, which we call sample and hold. Okay? Now, sample and hold says that we sample as before as in the sampling scheme, but then once we sample, we store it in a hash table, and we watch all the packets sent after that by that source. Okay? So it's kind of, think about it this way, right? The Gallup poll estimates whether Bush versus Gore by sampling households, right? By 1,000 households, and says Bush, Gore, Bush, Gore, Bush, Gore, and then they make an estimate of who's likely to win. But the problem for the Gallup poll is that the expense is sampling, going to those households. For us, sampling is not an expense because the households are tramping right through the polling booth, so to speak. right? So we might as well, once we've sampled somebody, watch all of them. And intuitively what happens is it's a variance reduction technique, because the variance comes in only at the first time. Once it floats into the cache, we've got it exactly and it's deterministic. Okay, so you can prove this. You can prove that the standard error, right, is basically order 1 over m, where m is the memory, while in standard sampling, it's 1 over square root m. It's not hard to believe because variance goes as square root, right? And so, but this is actually quite significant, right? So if memory is 10,000, the error is 1 over 10,000, the other one is 1 over 100. So that's order of magnitude. Now, Balaji Prabhakar at Stanford and some students sort of found a simple improvement of this, which we actually found useful in a Cisco chip, where he basically noticed that sample and hold, the small guys come in and they pollute the cache. So all you need to do is recycle the small guys and get rid of them. And so he calls that elephant traps, which basically it's sample and hold plus a recycling scheme. Okay? So again, the point here is the theme, right? It is important to find heavy hitters. Why? Because a lot of people would like to sort of figure out when attacks happen. They're often evinced by these people who send a significantly larger traffic footprint than the rest. So that's why it's useful, and there are many other reasons. You would like to do traffic engineering for the very largest flows, because 80% of the traffic is sort of dominated by. So that's the systems issue. So why? And it's not easy to do it's easy to do if you have infinite memory, but you don't have it, right? Simple sampling will work, but you can do better by adding a little bit of memory and processing. Okay, so this just illustrates our theme, and now let's get to the first of the two bigger topics, right, which is measuring microsecond latency. All right, so basically, when you tell people that people now care in the internet about measuring latencies down to microseconds, nobody can believe it. Because you say, look, my email took me 10 seconds. What are you talking about microseconds? Well, so in fact, the first wave of latency critical applications appeared about 10 years ago, and they were things like voice over IP, right, IPTV, and gamers. Gamers care, right? But if you look hard at the numbers, most people believe that as long as you get within 200 millisecond latency, all this class of applications are perfectly happy. So why microseconds? Well, you may not believe, but there's at least a sense that they're not the drivers for microsecond latency, right? All right, but what interesting people, now in all of these cases, it's a human being that's reacting to a message. And you can imagine how can a human being tell the difference between a millisecond and a microsecond? It's impossible. The fundamental shift occurs when machines sort of are sending messages to machines, and they can't tell the difference. Okay, so classic example is somewhat discredited after a crash is automated financial programs, right? So why do automated financial programs care, right? So the Dow Jones feed is giving the feed of stock prices, and you have two bankers, Merrill Lynch and let's say Smith Barney. And one of them has a lower latency link by maybe 100 microseconds. Okay, because it's a program, they can go ahead and see a cheap stock, bid up that stock before the other guy gets to it, and so there's arbitrage. And they are very conscious of that. You can look at the stock exchange, look at all the finance, and they're talking about microsecond traders, and edges, and all kinds of stuff. So this is very serious. I mean, the traders do care. In fact, the biggest markets for detecting low latency is in these automated in the stock exchange, and verticals like Cisco has verticals. So they are actually talking about less than 100 microsecond latency. They care.
They hold the stock only for 11 seconds.
Depends, right?
Average.
Right. The average is 11 seconds, but because they do a lot of short-term shifting, right, which is bad for the overall economy, but nevertheless, let's keep that aside. So, and also they want very small loss, because it turns out that if you lose one packet, it turns out that the canonical programs tend to have 200 millisecond timeouts, and that's a disaster from the point of view of all of these people. Okay? But to me, the more fundamental reason is high-performance computing. Okay? In high-performance computing, computers are working together with other computers in clusters to do large parallel jobs. That would be true in FedEx, drug discovery, like Southwest might be finding routes. So the big Fortune 500 companies are doing these things. Now, a cluster cares because every time you wait 100 microseconds, a computer is sort of wasting so many instructions, which it could be doing to do their job faster. Okay? That is fundamental. Now, hitherto, these two interconnects have been separate. The computers have had their own interconnects, right, like InfiniBand and Fiber Channel, and the internet has had Ethernet. But Ethernet has been fundamentally cheaper, so there's been a huge shift in the last few years to try to put all of this on top of Ethernet. But then Ethernet needs to have low latency and low loss. And of course, Microsoft knows that. And so the group I'm working with, they've included, is worrying tremendously about all these things, right? So, but either way, if you look at this, you really at least need to measure to know whether you're getting low latency and low loss. Okay, so with all of that motivation, let's define. It turns out I don't want to talk about these things except that for those of you who know networking, there are things like SNMP and NetFlow, but they're 2 cores. They have millisecond or second resolution, and you can store all the records, but you often lose all of them in NetFlow. So there's no really good solution. All right. Now, what people do today is that they go ahead and send these messages, right, periodically as test messages. They call them probes, and from one end to another, and seeing how long it takes, and they timestamp it, and that's their sort of external check that things are working well. But you can't send these test messages every microsecond. You can send them every millisecond because they take a lot. So, and then if you want to find out where the problem is, you have to do what is known as a join. You have to say, hey, I've sent these 2 messages, and both of them are taking latency, so possibly in the intersection of the 2 paths, there is a bottleneck. Right? But that's all. Now, what you're going to try to do is try to inverse this whole process and directly engineer this, as opposed to believing the network is a black box. Okay, so our model is basically going to be we're going to basically say every router in the world is going to add a little bit of hardware, right, to every link in the path, so that it can measure the latency on every link. So now, first of all, if there's a problem somewhere in the middle of the network, you directly know the answer. You don't have to infer the answer from black box. Secondly, if you want to find path metrics, you just add them up, right? Okay. So basically, in order to do that, what I want to do in this part of the talk is I want to show you a simple data structure that can help you find latencies on a link, right? And it's randomized or hash based, and we're going to calculate loss, delay, average, and variance. Okay, and so in order to do this, I have to explain and abstract the problem. Okay, so let's abstract the problem. So I'll give you a model. I'll show you why simple data structures do not work, and then I'll explain the algorithm. All right. So here is what we're going to do is we're going to segment the link. Remember, this is between 2 routers. Okay, or it may not be between 2 routers. And actually, the more common model. Okay, so and this is important. I haven't drawn it. So you have 2 things: a router and a link. The links are often very good. They hardly have any delays, and they hardly have any loss. Most of the loss is between the input port of a router and the output port of a router, okay, because there are queues and fabrics and stuff. So when I think of a link, this is the more important link I'm talking about, the link between the input port of a router and the output port. So don't think of the fiber optic link between routers, because that has almost no delay and almost no loss. Okay? So be aware that that's where most of the loss is. All right, so that's what I mean abstractly by link, but it looks like a link, so don't get confused. Okay, so you have 3 packets, a black, a gray, and a white, and so packets always travel unidirectionally, so you have to do it in 2 directions separately to find the delays on both links. And you're going to divide time into equal bins, and we typically use some measurement interval. Okay, so the packets go across, and the idea is that both S and R are going to maintain some state. Okay, so the sender maintains ds and the receiver maintains dr. Okay, and at the end of the interval, S transfers its state and then the receiver computes the measure based on some function of ds and dr. Okay, is that a simple model, easy to understand? Okay, so we're going to make a couple of assumptions. Okay, so we're going to assume the link is FIFO. First in, first out. Okay? And we can extend it. Now, within routers, you actually sometimes do stripe packets. Okay? But you often stripe it internally, and before they come out, you resequence, because TCP doesn't like it. So if you do it in certain points, you can make this assumption. Okay? We're going to assume that clocks are synchronized. That is, if this guy says 12 o'clock, right, then this guy is going to say 12 o'clock to within a microsecond. Now, it wasn't true a few years ago. Increasingly, routers are doing this. At least the Cisco Nexus does this, and it's microsecond synchronization. Now, across links between this end and this end, it's a little harder, because if you're used to something called NTP, it is millisecond. Rather, you say, what is this? Microsecond. Stuff. But there is a new protocol called 1588 that is hardware-based, that directly gets timestamps in hardware and bypasses a lot of the software, which is doing this too. So some of these assumptions are becoming true, and we're going to assume that a little bit of hardware can be put into routers. Okay? And the 5th assumption is very important, is if you could put a timestamp in every packet, the problem is trivial. all you do is record the send time at the input port, and the receiver takes a look at the send time and looks at its current time. And the trouble is that there is no such packet, right? And even if you did it, it's essentially linear overhead. You're adding this thing to every, and we're going to try to do better than linear overhead. Okay, so let's start by taking this.
Wait, George, I mean,
yes, go ahead.
If I had time sync across all the routers,
yes,
but then I could sample, but say I'll put this extra header in occasionally, or I'll put a pacing packet in occasionally.
You could do that too, but that's sampling. So let's talk about the two extremes. Both of them will come to the same thing. Either you put it on everything or you sample. And both of them are the existing work, which you're going to tell you why is not as good, right? Okay. So we're going to assume very little high-speed memory. We're also going to assume that processing, but the other assumption is that you can't really send a lot of messages between S and R. Because if you could just send arbitrary amount of information. And so routers don't generally like to send a lot of control information between this port and this port, right? So you can send a message every millisecond, but not every microsecond. All right, so just to get the numbers right, okay, just if you consider a 10 gigabit per second link, in 1 second, you basically, you can get 5 million packets. So the numbers are large. You can't afford to keep 5 million pieces of memory. And you can assume at most 1 control packet per millisecond, possibly even per second. Okay, so let's start with the simplest scheme, which is just computing loss. And loss is so trivial, you realize, why don't these router vendors do this? And actually, I don't know the answer, okay? So for example, if you have 3 packets, right, and one of them is lost, right, it's easy. You simply keep a counter at the sender, how much you sent, a counter at the receiver, how much you received, and at the end of the interval, S sends 3 to the other end, the guy subtracts and says 1 out of 3 was lost. Big deal, okay? So why can't you do that with latency? Well, so you kind of could, but the simplest way would be you simply keep timestamps at the sender. Remember, there's no timestamp in the packet. So you keep a timestamp at the sender, 10, right? And it was received at 23. The second packet was sent at 12, received at 26. Remember, they're synchronized. And 15 and 35. And at the end of the interval, you ship the entire truckload right to the other end, subtract and divide, and that's your average. Okay? But this is 3, but the real number is 5 million. So as you see 5 million, you say, well, maybe not. All right. And that's quite a lot of overhead. Okay, so it is high, and remember that timestamps per packet, and within a router you could add another timestamp per packet, but it's still the same linear overhead. You're adding, like a timestamp which is quite large, like 4 bytes or 8 bytes, right, per packet, and for 40-byte packets that is quite a lot of overhead. So even if doing it within per router, so you'd like to do better than this. All right, now obviously, as I told you in the beginning, there is a simple sample solution to everything, right? So obviously you could sample. So don't store all the timestamps, right? But let's say you sample the first and the third. So the first one is 10, the second one is 23, and 15 and 35, and you have to have a reasonable way to sample it, but that's easy. You can do content-based sampling. And now you take the 2 samples, send them to the other end, right? Hopefully you synchronize them with the corresponding received timestamp, subtract, divide by 2. Okay? So what's the problem with sampling? Typically, to get the numbers reasonable, you want something like 1 in 100 samples, and the number of samples is quite small in the end. You get about 250 to make your memory reasonable. Now, if you see that the variance reduces as the square root of the sample size, right? So it turns out that you're trying to get to microsecond detection. Right? These small sample sizes do matter. You would ideally like all the samples, right? If you could, right? Yes, go ahead.
Are you assuming there's no loss when this happens?
Good point. There is loss. So in this case, I'm just saying if there is loss, then some of the samples are lost, and you decide when you go to the other end. Let's talk about that when we talk about the real scheme. I don't want to talk about all the purported schemes before I talk about the okay. All right. So yeah. So this is okay, but we can do better. We can get much better standard error. All right. So now the simplest scheme you can do, right, is to basically is to simply keep a counter which is the sum of the timestamps of all the sender timestamps, 10, 12, 15, and the sum of the timestamps of all the receiver timestamps. So far, no loss. Assume no loss. Okay, for a minute. All right. So now you store the timestamp sums, and you also store the number. I didn't show it in the animation, 3, right? And now you simply take 23 plus 26 plus 35 minus 10 plus 12 plus 5, and it's just one counter, possibly 64 bits, right? Subtract CS minus CR divided by, and you have the number. So it's like, what is this talk about? Okay, well, as this we pointed out, the only issue is loss. Okay, so loss can actually do pretty badly, right? And let's see how badly loss can do. So the simplest counterexample, consider an interval of time t. T is big, like 1 second. 2 packets, one sent at half the interval, t by half a second, and the second one sent at 1 second. Both of them take 0 time, right? The first packet is lost. The sender measures 1 plus half, 1.5, right? The receiver just measures 1. So when you subtract the two, you get half a second. And if you don't do any other kind of thing, you divide by what? Divide by, even if the sender, if you divide by 1, you get half a second when the actual delay is 0. So you can be off by orders of magnitude by loss. Okay? And simple approaches like Bloom filters and all don't quite work. You do. So you can do error detection, but not error correction. So you can detect that you have a problem, but you would rather get some estimate when there's loss, as opposed to say, sorry, no. So yeah, by simply sending the counter, you can detect that there is a problem, but you would also like to correct. Okay? So now you're almost to the obvious idea now, right? So what's the obvious idea? We know that a single copy of this algorithm, right, can be detected to be wrong, but it can't be corrected. So, well, you run multiple copies, right? So it's pretty easy, right? No, but before we do that, let's talk about the theoretical perspective, right? From the theory point of this view, this is a streaming algorithm. But it's not quite the same as normal streaming algorithms. In a normal streaming algorithm, you have a stream of data, and you have a single point that computes a function on that stream. Max, min, median, whatever you want, right? Here, what happens is you have 2 streams. You have a stream of send timestamps and a stream of receive timestamps. Okay? And what you want to do is to actually do a function that coordinates corresponding points in the 2 streams. So you want to take, for example, the send minus the first receive minus the first send, the second receive minus the second send, and so on and so forth. So you have to coordinate those. And secondly, you can have loss. So these are 2 small things, but for example, just to show the theoreticians here, right, max is completely trivial in a standard, you simply keep the max. But you can prove, using a reduction to communication complexity, that it takes provably linear time, linear storage. So if you wanted to compute the maximum delay, right, you can prove that you have to keep all the timestamps, pretty much. So that's a big difference in model, right? So that's just for the theoreticians. If you're a systems person, you don't care, forget it. Okay, so go ahead. Just to compute the max of all the maximum latency. Okay, so imagine the maximum latency is the packet. There's one packet that takes a long time to arrive, right, in this million packets, the needle in the haystack, right? So is there a simple summarizing function? No. Okay, you can show this by reduction by Bar-Joseph, etc. Okay. All right. So what do we do for delay in the presence of loss? Okay, so what we're going to do is simply have multiple hash buckets, and the obvious idea, we're going to take packets and spread them across buckets. Right? So rather than put all our eggs in one basket or one bucket, we're going to spread packets across buckets. And now if some buckets get destroyed by loss, then hopefully other buckets will survive. So that's the main idea. So you take your first packet, it happens to hash onto the first bucket, and you store exactly the original naive algorithm. You store the sum of the timestamps and the number. So actually you store 10, and the second packet hashes onto the second bucket, so 12 goes to the second bucket. The third packet happens to go on to the first bucket again. Since it collides, there's no collision, you simply sum. Go ahead.
I mean, is this somewhat like quantiles would be robust to loss, right?
We'll talk about all the robustness. That's coming, right? So for the first thing is if there are at most 10 losses and you have 11 buckets, at least one will survive.
Isn't your notion of bucketing is it really corresponding with keeping quantiles in a sense? That
it doesn't really, because you're simply hashing uniformly. You're taking the packets and hashing based on their content. Now this is very important. You take some part of a packet that doesn't change, right? And that's important because the sender and receiver must hash in exactly the same way so that the correspondence is built in, right? So that's why the problem of otherwise you can't have them go to different buckets to get the wrong estimates. Okay, so, all right. So the third packet comes in and it goes into the second bucket, and so the first bucket has the sum of the 2 sense timestamps, so the ones that 10 plus 15. The second one is 12 plus 17. Now what's happened here? Well, it's easy. The white packet has been lost, right? And so it wasn't in that bucket. So now the summary data structure, the synopsis you keep the sum of the timestamps 25, but you also keep the number 20. So 29 and 2, but this guy has this telltale 1. Right? So you ship the summary to the other end, right? And now your combining operator is easy. Whenever you find the numbers don't match, right, you ignore that bucket. If the numbers match, you simply aggregate all of them and divide by the numbers. So in this case, there's only one bucket that works. You take 65 minus 29, divide by 2, right? Okay. So and that's basically the idea. And now it turns out that you have this very simple idea, and then you write a paper that complicates this and makes it more complicated in the following senses, right? To make it work, you have to do a little more complexity, but the idea is very simple. So first of all, this works, you can't afford a lot of memory. So how many buckets could you have? Maybe 100, right? So that suggests that you can only deal with 99 losses. But in real life, losses are rare. But once in a while, you might lose all packets, or you can lose a lot. So you really can't tell what the losses are. So what we now do is we bring back sampling into the mix, right? Because we are dealing with an adversary who's giving us unknown loss. So we're going to control the loss after sampling such that at least half the buckets will survive. So we'll get a good estimate from there. And now the next problem is we don't know the loss. If we knew the loss rate, we could make the sampling rate and adjust it. But we don't know the loss rate in advance. So now all we do is run log copies of for high loss, low loss, medium loss. So now we are completely resilient. In the internet environment, we hate to make assumptions. We don't know anything. So we'd rather just, and this one, and the net result is quite good. With about like some 500 buckets and reasonable amounts of chip real estate area, you can do a lot of this. Okay.
The summary goes through without the loss.
The summary goes through without loss. You're right. So the idea is, no, you're right. You could have done that, but you're right. So if the summary gets lost, you do lose the you do lose the estimate for that interval. So you're right. So there is in that case you're right. So there is. So let's see. So the difference is you could send it 5 times, and that's right, and random times, and that's probably something we should have said. Yes.
And do you perhaps want to exploit the fact that you have time in your favor? Like you could compute the summary at regular intervals. Because once you compute the summary, you can discard that information, and you have that information, right?
Right.
So the problem is if you keep collecting information in these buckets for a long period of time, I guess.
You don't. So every interval, I should tell you, every interval you reset everything.
Yes. Okay. So you just control that to
exactly.
match your loss rate somehow, and all that.
Right. So typically the intervals depend on, some manager will say, I want the intervals in a second, right? And I want the average latency in a second, and I also want the variance, right? So those intervals come from higher levels. But every interval you reset everything and start the whole algorithm again. All the counters go to 0. Okay. All right.
And that's triggered by the control packets?
Yes, exactly. Every time the control packets come in, we redo this. And we do have resiliency mechanisms to detect the fact that you synchronize them in case of losses and put sequence numbers on the control packet. But those are our control packets, so we could synchronize them. Okay, so the point behind this slide is simply that if you compare this to the active probe kind of approach, right? You get, a big order of magnitude difference given the bandwidth limits, and in order to be able to do the same kind of estimates, you get the red ones are just much smaller errors than you would with just sending messages periodically, because messages periodically you have only so much control bandwidth, so your sample size is so small that, well, here, especially when the loss is small, you pretty much get all the samples. So you get a perfect estimate. As the loss goes up, you can see the error goes up, but not as badly, right, as that. So at some point, though, if the error gets very bad, then it's going to degenerate to simple sampling, because it's like sampling once every control packet. So, all right. So far you say, all right, like average is kind of obvious, right? Because instead of taking S2 minus the received R1 minus S1 plus R2 minus S2 plus R and divide by N, you could simply take sigma Ri minus sigma Si divided by N. And that's obvious because it's a linear operator. Okay, but what about variance? It's much more interesting, right? Because a lot of people would like variance because it's not enough to know that your average delay is 10 microseconds. You really like to say that, look, in the 99% case, it never exceeds, like so much. You can't get the max, it's too hard, but at least getting a variance is useful. All right, so variance is not a linear operator, right? You're going to take the received timestamp minus the send timestamp, square it, plus the second received R2 minus S2 square, plus R3 minus S3 square. So it's not obvious how you could simply take the sum of the receives and the sum of them and square them, and most of the simple things don't work. Okay? Fortunately, right, there's, we just steal this idea from AMS, right, for estimating the second moment. And the idea is that operationally, I'll just describe it operationally. Normally what we did is at the receiver side and the sender side, we added the timestamps for everybody in the bucket. Now we're going to simply have another hash which takes the packet and decides whether to add or subtract. So we're going to take a timestamp and add or subtract with equal probability, right, from this counter. And so we're going to keep this up-down counter, right, for each bucket, and similarly the corresponding one at the receiver. And now we're going to take the two and subtract them, right, and we're going to simply divide by n, and that's going to be an estimate of the variance, and then you can get. So why does this work, right? So intuitively, what happens is it's fairly straightforward to see what's happening. So when you take this counter, so you're taking R1 plus or minus R1 plus or minus S1, and then you and you sorry. So sorry, you're taking the so each of these counters, instead of taking the send1 counter plus send2 counter plus send3 counter plus send4 counter, you're basically taking S1 plus or minus S2 plus or minus S3, and you're also taking R1 plus or minus R2 plus or minus R3. Okay, so when you subtract these two, you can collect them together as plus or minus R1 minus S1 plus or minus R2 minus S2 plus or minus R3 minus S3, and so on. So when you square, right, what's going to happen is you're going to get all the right terms, R1 square, sigma R1 square, and you're going to get you're going to get R1 minus, you're going to get exactly R1 minus S1 square, which you want, but all the cross product terms are going to disappear with equal probability, because you're going to get plus with equal probability and minus with equal probability. So in the end, you're simply going to get the sum of the Ri minus Si square, which is exactly the variance. Okay? So that's the AMS result, and so you directly get it. But the point from the hardware point of view is it's no more complicated than the other one. You just had to add one more hash, look at a bit, and subtract now instead of adding. So you had a subtractor as well as a adder. Yeah.
Is the plus or minus also coherent?
It has to be consistent. So that's essential, right? If you don't, you're screwed, right? So you're right. So the hash is again based on the packet. So that's what makes sure that when you actually keep R1 plus or minus R2 and he keeps S1 plus or minus S2, when you subtract it, that's what makes sure the signs of these two are the same, and that's important. Otherwise, it doesn't work. Yeah. So. All right. So basically, you can do this with we checked with our friends at Cisco, and there is standard chip sizes that are like very conservative, 95 millimeters, and this scheme will take like 1% of such an ASIC. Now it turns out that most chips have lots of gates today, so they do have gates to play, and it's a very reasonable proposition to make to them to do something like this. Okay. The FIFO model is still true between inputs and outputs of a router. You can deploy this by deploying this within single routers where most of the delay is, and then later get it across routers, and time synchronization is being done. All right. So again, let me just summarize this part. With rise in modern training in video, fine-grained latency, if you forget everything else, right, remember that suddenly microsecond latency is becoming interesting to us. We used to be a throughput factory in networks. Suddenly we're becoming, beaten up for latency. Right, and it's really interesting. It's changed a lot of the way. And we proposed LDAs. It's very simple to implement and deploy, and it's capable of measuring average delay and variance, loss, and microbursts. And what's the edge? Okay, so the edge is basically the number of samples. It's really it's a sample amplifier. It gives you a lot more samples than you would. Right, the edge, if there's no loss, you will have 1 million samples effectively. Right, it's the same result as you had. While you would have M samples, let's say 1,000. And that's much better and so it can reduce the error by the square root of the difference, which is quite a bit. Okay, all right.
Is it actually true that most of the delay is inside routers? I buy that almost all of the loss is coming inside routers because.
Okay, so the setting, a very good point. The setting here is often data centers, right, where the propagation delay is not significant. That's very important. Once you go to the wide area, that's not true at all. Yeah. So because banking, the high performance can be all within data centers. So actually, that context should have been said before. My mistake. Yeah.
So technically, AMS uses 4-wise independence. Right? So the corresponding hashing, can it be done that fast within a router?
Yeah. So we don't do their hashing. So in networking, we follow the Mitzenmacher style stuff. We completely ignore their hashing and just do what we can do in hardware fast. And our experiments say it just works great. So Mike has a lot of results with Sadan saying that various theoretical. We've not bothered to verify that we just simply do it. So that's a good point. We don't. The kind of hashing we do is typically like this, right? One of the simplest ways is we take we consider it as multiplication of the key by a random matrix of zeros and ones, and that seems to just work really well. And it's really easy because it's a network of XOR gates, and we can implement this really fast. So yeah.
Those results about entropy seem to rely on the application, right? So it might actually apply depending on what kind
it
of
probably applies, but
right?
it's going to take some. So most networking people have cheerfully ignored the reasons for 4i independence, and we just simply do it. And but it's a good point. At some point, somebody should verify that there is enough entropy to make this happen. But we expect that. We should have measured real traffic streams, and that's what we did. Okay, sorry. So much for 4a independence. But so now I want to completely change context, and the only way I can change context is tell you a story, so that you can erase all your memories of this previous slide, because we're going to change the context, change the measures, change the problem, and if you get confused with the previous part, we're in trouble. Okay, so my friend, I'm from India, and I had a friend from India whose mother came to visit. Old Sturbridge Farm, I think, in Massachusetts, and she had this little circle on her head that Indian women call a bindi, right? So an American came up to this friend's mother and said, "That's a beautiful thing. How do you do this?" And so my friend launched into this spiel about how Indian women, have sort of trained from birth to draw these beautiful circles, and they practice hard before a mirror. And as he was saying this, his mother sort of unpeeled this paste thing from her forehead, and he was so embarrassed, right? So the thing is, he was right. The old days they used to do things like this, right? But his model of the universe had shifted, right? So similarly, if you're not careful, right, we're going to completely change our model. So be careful. It's a totally new problem. So this is with Mike Mitzenmacher and Terry Lam, and it appeared in NSDI. Okay, so it's called Carousel. All right. So the problem at hand is that we have this deluge of interesting events coming to networks, right? Attacks are happening, packets are being dropped, and you have this manager who's trying to understand, make sense of this deluge of data, right? And the standard approach is to try to get a coherent view is basically sampling and summarizing. You either take a sample of some of the events, right? Or you summarize and you say you keep a count. Okay, but there are certain contexts where you really want complete information. Okay, so let's give you an example. So imagine a worm breaks out and attacks Microsoft. Well, actually, university is better. It cannot, by definition, attack Microsoft. Microsoft is sacrosanct. It won't. Worms know better than that. But let's but let's say universities, fair game. So they come to UCSD and they start infecting all these machines. And this is code red, and it shows you how fast it took over the world and how many machines it took over, right? So at that point, right, at the end of the or during the attack, managers would like to know not a sample of which machines were infected, not a count of how many machines were infected. They want to know which machines were infected. Your machine is infected, yours is not, and so they can remediate. So they want a collection of all of them. Another example is list all the stations of a particular type, the new ones deploying IPv6, deploying TCP/ACK, and a problem that I encountered many years ago and I was always haunted by is list all the MAC addresses, right? And so what's the issue, right? So what's the issue with this? So let's just let's make our problem concrete, although it applies to many settings, by the following simple setting, right? So the simple setting is you're trying to detect bad messages, right? And there is a device called an intrusion detection device. It's a detector of bad packets, right? Now each packet has a key, which is its source, let's say A, and some content which is somehow bad. There's a bad program there. Now, fortunately, the device has a signature, right, which is a regular expression on the content, which sort of decides that this is slammer, or which is a worm, or this is witty. So the idea is, as the packets are passing, the intrusion device taps on these devices, and it simply applies it in parallel to all of these signatures. And if it matches the red, the idea is it should send a little message with the red, with a flag saying it's red, and the source A. Okay, and similarly, it should send B, and it should send C. So at the end of the result, you should be able to get all your infected ones, and also which one they were infected with, so that you could go ahead and remediate that. All right. So this is a classic kind of issue. But so most of the work in intrusion detection is focused on fast matching. As you can see, that's a problem. But very few people have worried about the logging. They say, it's a boring thing, just log it, right? So, but under certain assumptions, logging is hard. So let's see why. So the model, right, the queuing model is as follows. Let me put a queuing model here. So there are n sources, and n is large, maybe 1 million. Okay? They're arriving at a queue at some very large rate, B, capital B, which is like, let's say 10 gigabits per second. Okay? The intrusion, the intrusion detection device is the hardware device, and it has limited memory. So it might have, say, 10,000 pieces of memory. And now it wants to eventually log everything to a sink that has infinite memory, right? But which has memory for them. But the logging speed is small, right? It's like, let's say, 10 megabits per second. So think about the two extremes. If you had infinite memory, right, it's easy, or n memory, you simply just store them and in leisure sort of log them to the source. If you had infinite speed, it's easy because as they come, you simply log them and you don't need a queue. But when you have two such constraints, right, you're in trouble. Okay, so just to make sure that you get the parameter space, the logging bandwidth is much smaller, several orders of magnitude smaller, right, than the arrival rate, and the memory is much smaller than the number of sources. So think of the memory as 100 and the thing as 1 million. What could you do? Right? Okay. Well, fortunately, there's one assumption. The systems are always cheap, right? So they change the model. Okay. So the assumption is that sources are persistent. An infected person is going to keep coming back. So if you miss him at this opportunity to log him, as long as you log him later within reasonable time, due bounds, right? Then you can. So you'd like to make up by playing games with time, so to speak. Okay. But how do you do this systematically? Yeah, that's the question. Right? So again, you can imagine that simple sampling will work, right? Just keep a finite memory, and by randomness of things, you should eventually put things over here, and eventually you'll get, if you wait enough time, you'll probably get everybody. But it's like coupon collectors, and coupon collector is not a very efficient way to grab all your coupons. There's better things you can do. Okay, so in fact, coupon collector tells you immediately that even in a simple random model, you have log n kind of inflation. Right, and you would like to do better than that. All right, so our results is we're going to show you a scheme called Carousel, which basically forgoes this log n model. And in fact, in any model of arrival, we're going to log all sources in close to optimal time. What is optimal time? N, million, divided by the logging speed. Right, will be a factor of 2 within that. And the standard approach is coupon collector, right, ln, and adding Bloom filters and other things doesn't really help. Okay, so now here is an animation, so it's easy to see what's the problem. Okay, so in this animation, you have two pieces of memory, right? And the sink is far away and it's going to be slow speed, and the packets are arriving here. So packet 1 arrives and it's stored in memory, no problem, we have space for it. Packet 4 arrives before we've logged because the logging speed is slow. We don't get a chance to log off it. Packet 3 comes in, oops, we don't have room for it, we drop it. Okay. Packet 4 comes in again. It doesn't really matter, but it's because we already have it. Packet 1 now finally gets a chance to be logged, right? Packet 4 moves up in the queue. Packet 1 comes in and is stored, and packet 2 comes in and is dropped. Okay? So notice that in this example that you had 4 sources and you only logged 2 of them, right? And I could repeat this example ad nauseum. Right? So if I was controlled by an adversary, the timing, right, I could make sure that some sources are never logged and never remediated. So this method is extremely susceptible to problems. If you assume a random model, yes, there's an LN inflation. But if you assume a deterministic adversary, right, it can be really bad. So basically sources 2 and 3 are never collected. 1 is logged many times. And in the worst case, n minus m sources can be missed. And remember, n is 1 million, m is 10,000. So you miss almost all sources. If you array, it's unlikely, but it at least could happen. And in security systems, you have to be really careful, right? Because these guys could conspire in timing and do stuff. So you really can't assume they're trying to help you get logged, right? That's not their job, right? Yeah. So it's not part of their job description, right? They won't get fired for. Okay. So now this is amazing. Now, theoreticians don't have this problem, but in systems, this is amazing fallacy that Bloom filters solve everything. Somehow they're just excited about Bloom filters. Yeah. Now, Bloom filters are a basically linear piece of memory. All they do is reduce the constant factor, right? It's a hash table, except that it reduces the constant factor by a factor of 10. So if you have a 10,000 piece of memory, right? How in the world is a Bloom filter going to help you log 1 million sources, right? It's not possible, but nevertheless, I have to go through this slide often because otherwise they'll say, why don't you use a Bloom filter? So let's just do it, okay? So imagine 1 comes in, right? And it's stored in the Bloom filter. There's 2 pieces of memory, and the Bloom filter just records a little trace that 1 was there. and then it's stored in the queue. 4 comes in, 4 is stored in both places too, right? And now 3 comes in and it is dropped because the Bloom filter is full. 4 comes in and rightly it's dropped because the Bloom filter says it's already there. 1 is logged, okay, 4 comes in, 1 is in the Bloom filter, 2 comes in, the Bloom filter is full, gone, okay, 4 goes on, and now what happens, now here's the problem. At some point, you can't just keep 1 and 4 in the Bloom filter forever, so you have to clear it. Right? If you clear it, I can repeat the same timing again and cause the same. So I don't even want to go through all these hundreds of pieces of animations. Hopefully, between friends, you'll agree. If there are adversaries in the audience, we can go through this again, right? Yeah. Okay. So whatever. Yeah, it takes too long. Yeah. Okay. So you can prove that it's really similar performance to a standard long. It really doesn't really help anything, right? And so the main point is the Bloom filter is necessarily small, and it reduces the duplicates by some marginal factor. That's all it does, right? All right. Okay, so now we still have to solve the problem. So, oops, in case I didn't mention that. So let's be inspired by an example from networking, which is something called admission control. In networking, it's a very common paradigm. If you can only handle, say, 10 megabits, and you have 100 megabits of arriving traffic, what you really want to do is admit only 10 megabits per second because you can give it service. And then the other guys have to wait on the edge of the network. It's like traffic and everybody else, okay? So even highway traffic does that. But the difficulty here is standard admission control, the sources cooperate. They help you. They say, all right, we'll wait at the entrance ramp, and but here these guys will be busting the ramps if they can. Like these are like infected nodes. They're not likely to follow any protocol you say. So what we would like is unilateral admission control. The question we ask is, what can a poor resource do, right, regardless of what the sources are doing? Right? So the sources can do any old thing. And so our approach is what we would call randomized admission control. And in essence, what we do is we're going to take the sources, break them up into sets, random sets, that are small enough to handle, and then, to be fair, we're going to cycle through all the sets so that to give everybody a fair chance. Okay, so that's the essence. So let's see an animation to see how it works. All right, so now we have some colors, which is great. Okay, so we have the same sources. We have the same Bloom filter. Yeah, it's useful, at least for, but we now have a little color filter too, right? And the color filter is going to start with red. And what we're going to do is we're going to magically color all the sources red and blue for now. And how do we color them? Think of hashing the keys. And if the hash lower bit is a 0, it's a red. If it's a 1, it's a blue. So we don't have to do anything special to paint these guys, but it just happens. Yeah. And now we have a color filter which says, now for the next X seconds, we're going to only log red sources. All right? So
require that you be able to have enough different colors.
Let's watch. The next question is how many colors. So let's know. So you're one slide ahead of the game. So just assume we know somehow magically it was 2. Okay, but we'll go to the next slide. All right. So what happens is 1 comes in, right? It's red. We are logging red sources. Fine. Put them in the Bloom filter. Put them in the queue, and so on. 2 comes in, and 2 is dropped because not the right color, right? So, okay, 3. Just in case you didn't notice it, it decides to telegraph your intentions by saying this explicitly. The 3 comes in, and 3 is allowed, and 3 is dropped, and 4 comes in, 4 is dropped. 2 comes in, it's dropped blue, and 3 comes in. 3 is logged, and now 1 comes in, and it is rightly dropped because it's already in the Bloom filter. So there's no point doing it again. Okay? And then 3 comes in, and it is again dropped because the Bloom filter. 4 comes in, and it's dropped. Okay? And so now what happens is that you've finally got all of these done, right? You've logged everybody you saw in your memory, and now what you have to do is you have to rotate the carousel, right? So you simply have to change colors, right, and become blue. And from now on, you log all blue sources.
Are you allowed to give this talk in Arizona?
Why? What did I do wrong? Okay, so and now you log blue sources, and now et cetera, et cetera. This is too painful, but anyway. So 3 is dropped, and so on. Okay. So all right. So, what did I do wrong?
How many colors?
Oh, how many colors? Okay. So sorry. So now come back to your question, right? So it could be that you picked the wrong number of colors. So you generally start with 0 colors, and then you sort of 1 color. Sorry. You start with 1 color. Oops. Yeah, and then you go to 2 and 4 and so. So the question is, when do you know that your colors are not enough, and then when do you reduce?
What actually worried me was an adversary can choose which color he would like to participate in.
No, because the hash is under your control. He doesn't know it.
Okay, so you're assuming a keyed hash. Okay.
Yeah. Been changing. Yeah. So yeah. I think that's a better model because given there are theoreticians in the room, like we want, go ahead.
Can you explain to me what you are using the Bloom filter for? What is it?
So yeah, it's a good point. So we're actually using it in two ways. One is we do use it to suppress duplicates within a color phase. So if somebody comes in and it's already in the queue, right? That's actually not much of a probability because it turns out it's such a small number that the probability of getting a duplicate out of n is very small. But there's a more important reason. We use it to sort of estimate when we are in trouble. Because what happens, it gives us, if the Bloom filter gets full, we know we don't have enough colors. And then we increase the number of colors. So it's kind of, it's a knob that we use. You think of it as a hash table, perfectly right. To me, it's just simply a smaller constant hash table, that's all. So there's a hash table and a queue. You have to keep a hash table to estimate the number of people currently who are currently...
Multiple numbers hashed to the same location in this filter?
Multiple numbers hashed to, yes.
They can, right?
Yeah, they can. But Bloom filters, that's a small false pop. Just think of it as a hash table.
As a Bloom filter?
I'm just using it as a Bloom
filter.
Okay. Just think of it as a hash table. Doesn't matter. Yeah. So in the end, what really matters is what's the size of the number of entries in this hash table, right? So
and how often?
It's easy to do, right? Because you can change colors in a microsecond by simply saying that instead of using the lower order 1 bit of your hash, you use 2 bits. So nothing has to be changed. Sources just get recolored automatically. Okay? So not the existing ones, and you have to clear everything and start again. Okay? So let's see what happens is 7 comes in, 7 is wrong color, 3 comes in, and 3 is the right color. It's stored, 4 comes in, and now 5 comes in, and something interesting happens, right? So 5 comes in, and 5 is red. But there's only 2 sources, and so you're in trouble. You need 3 at least, right? And so at that point, what you do is you say, oops, Bloom filter full, and you say increase the carousel colors, and you automatically recolor, right, to 4. And now you have to recolor all these guys, right? And they recolor, and then the right thing happens. So you'll keep recoloring until that's. And the point is, from an implementation point of view, it's nothing. You simply increase. It's a small little counter that you bump from 1 bit to 2 bits to 3 bits, and the hardware just does the right thing. There's no phasing, nothing has to be done. There's no going back and recoloring all the ones that have flown past. But you have to clear everything. And you sort of forgo your investment in logging so far. You say, hey, I don't care about that, right? And competitively speaking, you'll lose at most a factor of 2 because you're doubling, right? 1, 2, 4, 8. So, like in any binary tree, you'll only lose a factor of 2.
You'd expect the number of colors you need to be bounded by the ratio between the incoming rate versus the logging rate. But
the number of colors it's actually easy, right? So it's basically log to base. You can do m at a time, right? And so what happens is you can do m at a time, and so the number of phases you need is going to be at least n by m, right? Now in n by m, what you need to do just very simple math will give you the number of colors, right, based on these parameters. Yes.
So I haven't studied Bloom filters ever. But the only question
think of them as a hash table and a slightly compressed hash table that sometimes will will give you the wrong answer.
The only question I have about it is I can tell I can't add this entry to the Bloom filter.
Yes.
But I know that the Bloom filter, but I know it's not in the Bloom filter. Is that a simple operation?
Yes. Yes. So there is some there's a little bit of a probabilistic statement there, but nevertheless that's roughly true. Okay. So and now you redo this, and let's just skip through all of this because you guys sort of figure this out, and so yeah. All right. So let's just summarize this algorithm, right? So what is the algorithm, right? The algorithm is basically 3 steps. It's a partition step, which is like hash, and based on the color or the low order bits of the hash function, you partition. So more formally, right, you take hkx, which is the low order k bits of hs. It's a hash function of a source. You divide the population into partitions the same hash value. Okay, and then you iterate, because once you've hashed a color, you have to hash all the other guys, right? And so you simply take, and what is the time? It's a pretty obvious thing. If the memory is m, right, you might as well give enough time for that memory to be logged, m by l. And so after that, you want to wait. So the constants actually fall fairly nicely. Each iteration lasts t seconds, and the Bloom filter does weed out duplicates. It's marginally useful. Even if you didn't have it and had any other way to estimate the number, it'll probably work. So there are other ways you can use Flageolet-Martin and other kind of schemes to actually just estimate the number of distinct elements in a set, and that would just probably work fine too. If that number is too small, you could do it. And then you finally monitor. It turns out I've only shown you the uptick, but you also have to have a downtick. You have to learn that there are too many colors. If the worm outbreak sort of grew and then fell, then you really want to speed up, otherwise you'll waste time if you're trying to be optimal. So you want to make sure of that. Okay, and so you increase K if the Bloom filter is too full, you decrease K if the Bloom filter is too small, too empty. All right, so we did a number of experiments, and I'll just tell you one of them, right? So what we did was we took a real intrusion detection system called Snort. That is publicly available, right? You can go ahead and take a Linux box, load it in, and we basically took 10 gig links, and we took, but we couldn't. So what did we do? So we basically had to, we took 100 megabits per second links. We took a traffic generator that was sending stuff in with 10,000 sources, and we basically had the logging rate was 1 megabit per second. We ideally would have liked higher numbers here and higher numbers here, but because we couldn't get those numbers, we scaled down the system, right? And we did two cases. The source S was picked randomly, right, on each packet, and the other case was we went step through 1, 2, 3, 4 to 10,000, and then they repeat. And if they're working in concert, this might occur. Right? So it's not as unrealistic as you. And so neither of this is completely deterministically adversarial. Right? This is closer to random, and this is somewhat closer to bad cases. And so now what happens is, if you look at what's the measure, right? The measure is how long does it take to collect almost all sources, right? So as the number of sources goes up, right? So let's look at for 10,000, right? So with Carousel, it looks like within a little bit of time, right? You log all sources. But if you go and use standard Snort, which is basically random, it logs stuff. There's this long tail, and afterwards, just like all coupon collector problems, right? Towards the end, it gets increasingly longer to collect the rare stamps, so the rare coupons, and that's not surprising, right? And notice that the effect is much worse with the periodic pattern, right? And that's again not surprising. Random is more like a coupon collector, which a coupon collector likes. But when you have this periodic stuff, it works. So if you look at the numbers, right, that takes 300, and this one, while we pretty much get everything by 300, they get it by 1,500 seconds, and here it is, and so basically it's 5 times faster with the random and 100 times faster with periodic. Now, you can argue which is the right model, but we just show you the range, right? And so there's lots more experiments in the paper, lots more stuff, but I don't want to talk about it. Okay, so what's the big disadvantage of Carousel? Two big things that you have to remember. It doesn't solve every problem. First of all, it doesn't deal with one-shot logging. If somebody logs something once and never is spoken again, too bad, we can't deal with it, right? In infected nodes, it's okay, because if the infected node goes away, then perhaps we're not interested in it. So we can possibly make that argument. So you have to be careful. We don't get something for free, right? And similarly, it's probabilistic. We really get, the final theorem is we get 99.9% of all sources within this time, in competitive time. The last 1 or 2 we might still lose. So we get almost all, right? But it's not perfect logging. Okay, so it is, we believe, applicable to a wide range of monitoring tasks with high line speed, low memory, and small logging speed, and where the sources are persistent, right? And it's a form of randomized admission control.
IDSs? I thought most IDSs.
There are. So tipping point is close to 10 gigabits now. So there are a few, and there are hardware and that are doing pretty well. Then the company that Juniper bought, NetScreen, is also pretty good. So people are increasingly beginning to think that it should be packaged into routers. Cisco IDS has been struggling for a long time to go from 2 to 10. They'll get there. Okay, so let me just tell you the edge, and then I'll be done.
Yeah. More colors.
Yeah.
Do you lose a lot of stuff?
So what you do is you simply lose you just ignore all the logs that you've sent so far. It's like you start a new experiment.
So if you keep thrashing between more and less.
You have to be careful. So you have to make sure that, so you're assuming that the distribution is semi-stable, right? If it's changing rapidly, the population, you could thrash. So there's some assumption built in here that the number of sources changes slowly, and we react very slowly to the number of sources too. So if it does change fast, we'll work on some upper bound on that. So we might be slower, but it's not clear what optimal means in that case. So a real omniscient algorithm, if it could maybe do significantly better in a period of great churn, which by constantly changing the number of sources. Because when we sense it, we will take some bound for a while and work, and then we'll come down only much later. So there is room for play here, right? In a theoretical sense. Okay, so let's just finish up and say what is all this about the edge, right? So if you look at Carousel, right, it's a factor of 2 from the optimal to log all sources versus the standard coupon collector, right, is ln n by m. So remember, the actual edge could be infinite in an adversarial model, but let's put that aside and let's and give them ln n by m. So if you take n is equal to 1 million and m is small, the edge is close to 14. We could be 14 times faster to log almost all sources. Okay. Now compared to the random arrival model, which is like simple sampling, LDA sort of gives you n samples versus m samples. So if n is a million and m is 10,000, the edge is close to 10. Significant. Why 10? Because you take the square root of this number. Okay? And sample and hold is order 1 over m versus 1 over square root m. So if m is 10,000, the edge is 100. So again, the edge is simply what's the corresponding measure for simple sampling and how much, and what is the advantage of doing a little bit in hardware. And the claim is it's significant. You don't add too much in gates, and so why shouldn't you do it? Okay, so in terms of LDA streaming, lots of work on streaming algorithms. Less work that I know of, and I've asked Muthu and a few other people on two-party streaming algorithms, where there's some coordination between these guys, right? There's a lot of work in network tomography, which joins the result of black box measurements, but we are solving the inverse problem. We are directly instrumenting things as opposed to inferring where the problem is, right? So carousel, it's a very simple idea. The theoreticians are really interested. Basically it's randomly partitioning a large set into small enough sizes. So, and then the main idea is iterating through the sets, right? It's the only place I've seen it, and I would love to get more, is the Alto scavenger. Butler Lamson many years ago wrote a paper in the Alto where if they got too much stuff on disk and they were trying to rebuild the file index, they had to do this random divide and conquer. And they sort of took a random partition in smaller and smaller amounts till the size, the number of file set could fit into existing memory. Then they rebuilt it for the rest, and they cycled without keeping any memory. But it's a different problem because we have two limits. They had only one limit, memory. We have memory and bandwidth. But there's some idea there. Okay, so summary is the big theme. Now let's go back to the 20,000 foot level. So I think. For the students here, I think monitoring networks for performance is a big deal, right? That's what the world cares about. Pushing packets faster is nice, but people will do this. But all this stuff is still unknown. And there's a number of problems, and they're not quite just keep a counter, right? You have to do interesting things, right? Find latency, and randomized or really hash-based streaming algorithms really can offer cheap in-gate solutions at high speeds. So, it would be nice. And I described two simple hash-based algorithms I hope you'll remember, right? If you remember a one-line summary of LDA, all you're doing is aggregating the timestamps by summing, and you're hashing to withstand loss. That's the one-line summary. And the main idea in Carousel is you hash to partition the input set into smaller sets, and you cycle through the sets for fairness. Okay, that's the main idea, and just I had to remember it suggested a band, so there should have been some music here, but I don't know how to play it. So this is a silent band, and it's called The Edge. Okay, so I hope you remember that. Thanks. So any questions? Yes.
Random, do you mean pseudo-random, or do you have a good source of randomness?
Right. I don't assume a good source of randomness at all in any of this. They're hash-based. So the only thing we randomize is in the analysis, we assume that, we don't assume any four-way, we assume perfect, in classic Cavalier networking style, we assume that the hash is completely uniform. Right, and so ideally, probably all these results could be strengthened with twisting Michael's arm a little bit, to four-way independence or two-way or six-way, but we just ignored that. So we just use simple uniform. So the only one that might require a source of randomness is sample and hold. Sample and hold, you're actually sampling a packet, and that one requires a source of randomness. But ideally, even that could be hash-based. You could look at the packet and take some piece of the packet, like its source address, and you could do a hash on that. If the bits are less than so and so, these values, this set of values, you could sample it or not. So in some sense, you don't need a source of randomness. So I think networking people would prefer that, because our experience has been, even from doing Ethernet and other stuff, it's very hard to do physical. The only real randomness that works is to use some source of physical randomness, like short noise or something, and it's very hard. So the first Ethernet implementation is all locked up, so our experience has been really terrifying. So we would rather use hash-based algorithms, right? So hashing seems to be fine, assuming enough entropy in the stream. And so that's our uniform experience from, 10, 15 years, that it just seems to be fine. So, and we should go and dot the I's and cross the T's and check, but we haven't done it. Yeah, so any other questions? While the band keeps playing silently.
Thank you very much. George is going to be here for next Friday. So.